Hey, fellow devs. Ready to dive deep into cryptography? It's everywhere in our code, but most of us just use libraries and frameworks, right?
Right. We trust those tools, but wouldn't it be cool to really understand how they work under the hood? Like, what's actually going on when we encrypt data?
Totally. Today, we're going to break it all down, starting with the absolute basics. Because even the most complex crypto algorithms are built on simple ideas.
Exactly. Let's start with XOR. It's a fundamental logic gate, and it's like at the core of so much in crypto.
Okay, XOR. I remember that from, my Computer Science 101 class, but refresh my memory. Why is it so important for cryptography?
Well, think of XOR like a light switch, right? You've got two inputs. If they're the same, both on or both off, the output is 0, the light's off.
Makes sense.
But if the inputs are different, like one on and one off, then the output is 1, the light's on. Now, apply that to data,
Okay, I'm following. So we've got our data, and
and you XOR it with a secret key. Each bit of data gets XORed with the corresponding bit of the key. What you end up with is ciphertext. Totally scrambled, looks like gibberish.
So it's like flipping bits based on the key.
Yep. And the cool part is, if you XOR that ciphertext again with the same key, you get the original data back. That's the magic of XOR.
So it's reversible. I
Yeah.
see how that's useful for encryption and decryption. But real-world algorithms are way more complex than just XOR, right?
Of course. XOR is just one building block. Like, think of substitution
Oh,
ciphers.
yeah, where you swap one letter for another like a secret code.
Exactly. Or the classic Caesar cipher where you shift letters down the alphabet by a certain number. Simple, but you can combine these techniques with XOR and other operations to create more sophisticated ciphers.
Right. So these simple concepts can be layered to make something strong. I'm starting to see how it all fits together.
Yeah, and that brings us to the two main categories of encryption: symmetric and asymmetric.
Okay, let's break those down. What's the difference between symmetric and asymmetric?
Symmetric key crypto is like having one key for your house, and everybody uses the same key to lock and unlock the door.
Makes sense. Simple and efficient, but
But if the key falls into the wrong hands, everyone's in trouble. That's the main challenge with symmetric crypto: secure key distribution. Now, asymmetric crypto, well, that's a whole other story.
okay, so symmetric is like one key for everyone, and asymmetric.
Hmm.
Well, I guess we'll have to wait for part 2 to hear about that.
Exactly, stay tuned.
But before we move on from symmetric, I'm curious about stream ciphers and block ciphers. What are the key differences?
Okay, so imagine a stream cipher like encrypting a live stream of data. Each bit gets encrypted as it flows, using a continuous stream of key material.
Got it. So it's real-time encryption, perfect for things like video calls or streaming media, right?
Exactly. Now, block ciphers, on the other hand, chop the data into fixed-size blocks and encrypt each block individually.
Okay, so like dividing the message into chunks and encrypting each chunk separately? But wouldn't using the same key for each block make it vulnerable? Like, wouldn't patterns emerge?
You're thinking like a cryptographer already. That's where the initialization vector, or RV, comes in.
Oh, right, the IV. What does it do again?
It's like adding a secret ingredient to each block before encryption. So even if you use the same key, each block gets encrypted differently.
Ah, I see. So the IV ensures uniqueness, preventing those patterns. But why not just generate a random IV every time? Wouldn't that be more secure?
That's what you'd think, right? But here's where it gets counterintuitive. Remember the birthday paradox. The odds of two people in a room sharing a birthday are surprisingly high. Same thing can happen with IVs.
Okay, so if we randomly generate IVs, there's a chance of collision, and that weakens the encryption.
Precisely. So often, using a sequential IV is actually more secure. It eliminates the risk of accidentally repeating the same key stream.
Makes sense. So we got to think about these things carefully when choosing how to implement encryption. Now, what about those block cipher modes? Are they all created equal?
Not at all. The simplest mode is ECB, Electronic Codebook. It encrypts each block independently with the same key. Easy to implement, but
But there's got to be a downside.
big downside. If two blocks in the plaintext are the same, their ciphertext will also be identical. You start to see patterns, which can be a security weakness.
So it's like a basic substitution cipher, not very secure.
Right. That's why we have modes like CBC, cipher block chaining. It adds an extra step. Each block is XOR'd with the ciphertext of the previous block before encryption. It creates this chain reaction that makes the encryption much stronger.
Okay, so CBC is like linking those blocks together, so each one depends on the ones before it.
Yeah.
That's smart. So choosing the right block cipher mode is important. It all depends on the sensitivity of the data we're protecting. But what about that key distribution problem we talked about earlier with symmetric crypto? How do we securely share the key in the first place? I mean, that's a big deal, right?
Huge deal. And that's where asymmetric cryptography comes in. But we'll save that for part 2. Asymmetric crypto. It was like the secret sauce that makes so much of the internet possible.
Okay, so spill the beans. What makes it so special?
Instead of one key, you have two. A public key and a private key. They're mathematically linked, but you can't derive one from the other.
Uh-huh, so that solves the key distribution problem, right?
Exactly. You can share your public key with the world, and anyone can use it to encrypt a message that only you, with your private key, can decrypt.
So it's like having a public API endpoint.
Mm.
Anyone can send data to it, but only the server with the private key can actually process it.
Perfect analogy. It's the foundation of secure communication online.
Okay, I'm starting to see the power of this,
Mm.
but the math behind it,
Mm.
that's where I get a little lost. How does it actually work?
It's pretty mind-bending stuff involving prime numbers and modular arithmetic.
Prime numbers, okay. I can remember those. But modular arithmetic, what's that all about?
Imagine a clock. You go around in a circle, right? So if it's 10 o'clock and you add 5 hours, it's not 15 o'clock, it's 3 o'clock. You wrap around.
Right, you go back to the beginning.
That's the essence of modular arithmetic, working with remainders. And it turns out this kind of math is perfect for creating those linked key pairs. It ensures that the operations are easy in one direction, but practically impossible to reverse.
So it's like a one-way street for the math. I can see how that'd be useful for security.
Exactly. It's hard to break the code if you're going against the flow of the math, so to speak.
This is fascinating stuff. But asymmetric crypto isn't just about encryption, right? It also powers those digital signatures we hear about.
Absolutely. Digital signatures are like cryptographic seals of approval. They verify that a message is really from who it says it's from and that it hasn't been tampered with.
Okay, so like when I download software, and I want to make sure it's actually from the developer and not some malicious imposter.
Exactly. Digital signatures give you that confidence. And to understand how they work, we need to circle back to hashing.
Right, hashing. It's about creating those unique fingerprints for data, like a digital thumbprint, right?
Precisely. You feed any data into a hashing algorithm, and it spits out a fixed-length string of characters. No matter how big or small the input, the hash is always the same size. And it's practically impossible to reverse the process.
So you can't recreate the original data just from the hash. It's a one-way function.
Yep. Now, to create a digital signature, you first hash the message you want to sign.
Okay, so you're not encrypting the entire message, just its hash.
Right. Then you encrypt that hash using your private key. That encrypted hash is your digital signature. You send it along with the original message.
So the recipient gets both the message and this encrypted hash, the signature. Then what?
They use your public key to decrypt the signature, revealing the original hash of the message. Then they hash the message themselves and compare the two hashes.
If they match, it means the message is authentic and hasn't been messed with.
Pretty clever.
It is. And because only your private key could have created that specific signature, it also proves the message came from you. You can't deny sending it. So it provides non-repudiation. That's crucial for things like online transactions, legal documents, all sorts of things.
Absolutely. It's all about trust and accountability in the digital world. But you might be wondering, how do we know that your public key is actually yours? How do we prevent someone from impersonating you with a fake public key?
That's a good point. It seems like there's a missing piece here. How do we establish trust in the public keys themselves?
That's where certificate authorities, or CAs, come in. They're like the trusted notaries of the internet.
Okay, I've seen those names pop up in browser warnings,
Right.
but what exactly do they do?
They issue digital certificates, kind of like electronic passports for public keys.
So it's like an ID card for your public key, vouching for its authenticity. But how do we know we can trust the CA itself? It seems like a chicken and egg problem.
Good question. There's a whole hierarchy of trust built into the system. It starts with root CAs, highly trusted entities whose certificates are pre-installed in our operating systems and browsers.
Okay, so we're basically trusting those root CAs implicitly.
To a certain extent, yes, but there are checks and balances in place. These root CAs then issue certificates to subordinate CAs, who can issue certificates to individuals and organizations. It's a chain of trust, and if one link is broken, the whole chain is suspect.
So there are mechanisms to revoke certificates if they're compromised.
Exactly. It's not a perfect system, but it's what we have to establish trust in the digital world.
Makes sense. We need some way to verify identities online, and CAs play a vital role. So we've covered encryption and authentication. But crypto isn't just about protecting data in transit, right? There are also ways to hide information in plain sight, like with steganography.
Right. Steganography is all about hiding messages within other data, like images, audio files, even text. It's like hiding a secret message in a picture of your cat.
Now that's sneaky. How does that even work? Is it like invisible ink for digital data?
Not quite invisible ink, but the concept is similar. You subtly modify the data in a way that's imperceptible to humans, but detectable by software with the right key.
So you're tweaking the data without changing how it looks or sounds.
Yeah.
I can see how that'd be hard to detect. But why use steganography instead of just encrypting the message? What's the advantage?
It adds another layer of secrecy. Someone might intercept an image with a hidden message, but not even realize there's anything unusual about it. Encryption protects the content of a message. Steganography hides the very fact that their eye asks a message.
So it's like hiding in plain sight. Encryption is locking a message in a safe, and steganography is disguising the safe itself. Pretty cool. But how is steganography actually used? Is it just for spies and secret agents?
It has legitimate uses too, like digital watermarking to protect copyright. But yeah, it can be used for covert communication, and unfortunately, criminals use it too to hide data.
A tool can be used for good or bad. Makes me think of another fascinating crypto technique, the Diffie-Hellman key exchange. It's about establishing a shared secret key without actually transmitting it, right?
You got it. Diffie-Hellman is like magic. It lets two parties agree on a secret key, even if someone is eavesdropping on their conversation.
Okay, now that sounds like something straight out of a spy movie. I'm definitely intrigued. Break it down for us. How can you establish a shared secret without actually sending it?
It's all about some clever math and a kind of cryptographic dance. Imagine we're in a crowded room and want to share a secret without anyone else knowing. We can't just shout it, but we can use Diffie-Hellman to agree on that secret without anyone else figuring it out.
Okay, so walk me through this cryptographic dance. How do we actually do it?
First, we need to agree on a couple of things publicly: a prime number and a generator. Think of them like the starting ingredients for our secret sauce.
Okay, prime numbers, I kind of remember those from math class, but what's a generator in this context?
It's a number that helps us create a sequence of numbers that wrap around, kind of like that clock analogy we talked about with modular arithmetic.
Okay, got it. So we've got our public ingredients, the prime number, and the generator. What's next?
Now, here's where the secret part comes in. Each of us secretly chooses a random number. This is our private key.
So two secret ingredients, one for each of us.
Exactly. Then we use our private key, along with those public ingredients, to do some calculations. The result of those calculations is our public key.
So we each have a public key and a private key. And the public keys, we can share those openly.
Yep. We can exchange them however we want, even shout them across the room, and it doesn't compromise the security of our secret.
Okay, I'm following so far. But how do those public keys help us establish a shared secret?
This is where the magic happens. Each of us takes the other person's public key and combines it with our own private key in another calculation. And the amazing thing is, we both end up with the same shared secret key.
Wait, what? So even though we never exchanged our private keys, we were able to generate the same secret key just by using each other's public keys. How is that even possible?
It's the beauty of the math. The way these calculations work with the prime number and the generator, it ensures that we both arrive at the same result, even though we're starting with different private keys.
That's mind-blowing. And the eavesdropper, even if they see all the public keys and the prime number and generator, they can't figure out our shared secret.
It's extremely difficult for them to do that. It would take an insane amount of computing power to crack it.
So we've essentially created a secret communication channel right in front of everyone, but only we know the key to unlock it.
Exactly. It's like speaking in a code that only we understand. And once we have that shared secret key, we can use it for secure communication.
We can use it for symmetric encryption, right? Like those block ciphers we talked about earlier.
Exactly. Diffie-Hellman is the bridge that lets us securely exchange keys for symmetric encryption, even in the presence of potential eavesdroppers.
This is incredible. It's like a cryptographic handshake that establishes a secure connection. No wonder Diffie-Hellman is used in so many things, like TLS for secure websites and SSH for remote access.
It's a cornerstone of modern cryptography for sure, and it really highlights the power of math to solve real-world security problems.
This has been an amazing deep dive into cryptography. We started with the basics, like XOR and simple ciphers, and explored how those building blocks combine to create powerful tools for encryption, authentication, and even hiding data in plain sight. It's clear that cryptography is essential for building secure and trustworthy systems. And for us developers, understanding these concepts is crucial for protecting user data and building applications that people can trust.
I totally agree. It's not just about blindly using libraries and frameworks anymore. We need to understand the principles behind them so we can make informed decisions about security. We have a responsibility to use these tools wisely and ethically to create a more secure and resilient digital world.
Absolutely. So to all our fellow developers out there, keep learning, keep experimenting, and keep building secure and amazing things. Until next time, stay curious.